This is Unit 3, Topic G, and in this section we're going to talk about two very famous theorems in math. The first one's called Rolle's theorem, and here's the statement of the theorem. If f of x is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, means the derivative exists on that whole interval, and also f of a equals f of b, then f prime of c equals 0 for at least one number c in the open interval from a to b. Like a lot of theorems, it's very dense, packed with a lot of information, but drawing a picture can help us to interpret it. So let's begin by making sure we draw a function that satisfies all of these conditions, the hypothesis or the if part. I'm going to mark off a closed interval, or just an interval from a to b. And I need to draw a function that's continuous, so no jumps, breaks, or holes. Differentiable, so it has to be nice and smooth, right? No vertical tangent lines, no sharp peaks. And f of a and f of b have to be equal. So let's go ahead and start by picking a y value. Let's just make it right here. There's the y value at a, and I have to use the same y value at b, since f of a equals f of b. All right, just draw any continuous differentiable function you want between a and b. Sorry about that, calm those dogs down. All right, so we've set our function up. It has to go through both of these points. So again, I'm going to draw any smooth, continuous differentiable function that goes through both points. Doesn't really matter what it looks like. Maybe I'll just make mine like this. Again, it was continuous, no jumps, holes, breaks, asymptotes, and it's differentiable. There's no vertical tangent lines, no sharp peaks in there. All right, so I've satisfied all of the hypotheses. The conclusion is that f prime of c is equal to 0. In other words, the slope of the tangent line is 0 for at least one number c in between a and b. Now, the way I happen to have drawn this one, there's actually two of them, right? Here at this maximum, there'd be a horizontal tangent line. So that would constitute one of the values of c. Maybe I'll call it c1 since there's going to be another. And this point as well would have a horizontal tangent line. So that's another possible c value. I'll call it c2. There might only be one c value that works. There might be 50 of them. But what we're guaranteed by Rolle's theorem is that there will be at least one of those places where the derivative or slope of the tangent line will be 0. All right, so we're going to look at a couple of examples, and we're going to ask ourselves the question, first of all, does Rolle's theorem apply? In order to answer that, we have to verify that all of the hypotheses are satisfied. So if all of these three things are not satisfied, then Rolle's theorem isn't even applicable, and there's no point in trying to find the c value. Okay. If it is applicable, then we're going to try and find that c value guaranteed by the theorem and just draw a quick graph to illustrate it. Okay. If not, we'll use a graph to illustrate why it doesn't work. All right, so here we go. Our function x minus 3 times x plus 1 squared. We'd like to illustrate Rolle's theorem on the interval from -1 to 3. So I'm going to check the three things that make Rolle's theorem applicable. First of all, is it continuous? Well, in this case, although it's not multiplied out, f is a polynomial, right? If you multiplied it out, you would see that. And polynomials are continuous everywhere. No denominators, so no place where the function doesn't exist, no problems. Next, I have to show that it's differentiable. Polynomials actually are differentiable, but I'm going to need the derivative anyway, so let's go ahead and calculate our derivative. And then we can show that it exists everywhere. Although I really do have a choice, I could multiply this out. I'm just going to go ahead and use a product rule. It's not that complicated, right? If I do f is equal to x minus 3 and g is equal to x plus 1 squared, then f prime would be 1 and g prime would be 2 times x plus 1. There is a chain rule there, but it's just times 1, so I won't even bother to write it. And that means that my derivative is fg prime 2 times x plus 1 times x minus 3 plus gf prime, x plus 1 squared. I am going to go ahead and multiply this one out. Again, I'm going to need to later anyway, so I might as well take the time to do it now. Let's see, that would be x squared minus 2x minus 3 plus x squared plus 2x plus 1. And we'll finish up a little bit of algebra here. And we get 3x squared minus 2x minus 5. That clearly exists for all x values. There's no x I could plug in there that would cause a problem. So I'm going to say this is differentiable everywhere. All right, the third condition for Rolle's theorem was that f of a must equal f of b. So in my problem, the a and the b up here are the endpoints of the interval. So I'm just going to plug in f of negative 1. Oh, excuse me. Yeah, that's right. I'm going to plug in f of negative 1 and f of 3. And show that they are the same. If I go back up to the beginning, notice if I plug in negative 1, I'll get a factor of 0 right there. So 0 times whatever is still going to be 0. And if I plugged in 3, I would get a 0 in this first factor. So the product again will be 0. And so yes, f of a is equal to f of b. So since all three of these conditions are met, I'm going to say that Rolle's theorem applies. All right, since Rolle's theorem applies, we're supposed to find the c that's guaranteed. The c is the point where f prime of c is equal to 0, right? That's what the theorem guarantees me. And so if I take my f prime, which I have down here, and just plug in a c, and say that would be 0, let's see, I think that factors. What have we got here? 5 and a 1, negative and a positive, that would be negative 2c in the middle, so that one's good. So c equals 3/5, and c equals negative 1. Now be careful with your c values. Remember that c must be in the open interval from a to b in order to satisfy the theorem. 3/5 is definitely in the open interval from negative 1 to 3, but negative 1's not. It's in the closed interval, but not the open interval. So only the 3/5 is in that open interval. The negative 1, although it does have a derivative of 0, isn't the point that's guaranteed by Rolle's theorem. All right, as far as showing the problem using a graph, I'm just going to use a calculator graph to do that. Let's go ahead and graph our original function. And as far as a window, I don't need to look all that big. Let's go a negative 5 to 5. Well, actually, you know what? Let's just use the, I didn't mean to do that. I'm going to redo my window. Let's just use the window that's given to us here from negative 1 to 3 on the axis. On the y's, oh gosh, let's try -5 to 5. That looks like I should have gone a little bit lower. Let's go down to -10. And we can clearly see at the endpoints, they're both the same y value, both equal to 0. And right there is that point where we've got our horizontal tangent line. All right. I had to fix something there. I was just looking at that graph again, realizing that this point right here doesn't look like an x value of 3/5, and my algebra was bad there, wasn't it? That should have been 5/3, not 3/5. Sorry about that. So, in fact, C would be 5/3, and now if I were to actually take a look at this, between 1 and 2 is where that horizontal tangent is. So that makes more sense. All right, let's try this a couple more times. In our next example, f of x is the cotangent of x, and the interval is from -π/2 to π/2. I want to show that it's continuous and differentiable. So first of all, if I just keep in mind that cotangent is actually cosine x over sine x, I know that this is going to be undefined anytime sine x equals 0. And although there are a lot of places where sine x equals 0, one of those places is if x equals 0. And x equals 0 is within the interval. Therefore, I have to say Rolle's theorem doesn't apply because there's a discontinuity at x equals 0. And I'm done. Once I know the theorem doesn't apply, I'm not even going to look for the c value. All right, what about this one? The function is x to the 2/3 minus 1, and the interval is from -8 to 8. Once again, those three things I have to check, right? Continuous, differentiable, and the endpoints have to have the same y value. If I look at continuous, yes, f is continuous. There's no x value that would be a problem here because it's a cubed root. Positives, negatives, doesn't matter. So f is continuous everywhere. So condition 1, we're good. Condition 2, f has to be differentiable. So let's look at f prime. That would be 2/3 x to the -1/3 minus 0, or 2/3 times the cubed root of x. And that derivative is going to not exist if x is 0. And 0 is within our interval. So once again, I'm going to have to say there is a point in the interval where this function is not differentiable. So Rolle's theorem does not apply. All right, so our first theorem, Rolle's theorem, you can kind of see how that works. Let's look at our second theorem, the mean value theorem. This one says that if f is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, then there exists at least one number c such that f prime of c is equal to f of b minus f of a over b minus a. Notice that the hypotheses are not quite as stringent this time. I have to have continuous and differentiable, but there was no requirement that f of a equals f of b this time. So let's go ahead and once again in my picture I'm going to mark off points A and B. And they don't have to have the same y value, so I'm going to pick different ones. There's f of A, and there's f of B. And I'm just going to draw between those 2 points a continuous differentiable function. No jumps, breaks, or asymptotes, no vertical tangents, or sharp points. So I'm just going to make this fairly simple. Let's just do something like this. All right. What the theorem, the mean value theorem, guarantees me is that I have at least one number c such that the derivative, f prime of c, is equal to all of this. Now I'm sure that you recognize that as a slope formula. It's just the slope of the line that joins a f of a with b f of b. So I could just sketch in that line. Maybe I'll just do the segment in here. And the slope of that line would be this f of b minus f of a, that's y2 minus y1, over b minus a, x2 minus x1. What the theorem guarantees is that there's some point here in between a and b such that the derivative is the same number. Now, of course, the derivative is the slope of the tangent line. So this is saying that somewhere in here, the slope of the tangent line to the graph is exactly the same as the slope of that line we just drew. If we sort of play around with this just a little bit, maybe right about there, the tangent line would be parallel to the pink line that I just drew. And this point of tangency right here is going to be the c value guaranteed by the mean value theorem. It's the point where the tangent line slope is equal to the slope of the line between the 2 points. All right, we're going to do the same thing we did with Rolle's theorem. We'll look at a couple of examples and determine, first of all, are the conditions satisfied? And if so, we'll look for that point c that's guaranteed by the mean value theorem. So my conditions this time are just that the function has to be continuous and differentiable on the interval. And first of all, we've got this function on the interval from 1/2 to 2. So first condition, continuous. Well, clearly this function has a discontinuity at x equals 0, but 0 is not in the interval, so that's okay. So I'll remark discontinuous at x equals 0, but okay on the entire interval from 1/2 to 2. So we're okay with a continuous. Secondly, is it differentiable? Again, on that interval, and this one only has to be the open interval. Well, let's find the derivative to determine that. Let's see here. I'm actually going to simplify this thing before I take the derivative. X divided by x would be 1, plus 1 divided by x would be x to the negative first. So my derivative would be just 0, and then negative 1 x to the minus 2, or negative 1 over x squared. Same issue here, right? That derivative fails to exist if x equals 0. But since 0 is not part of our interval, it's okay. And I only really need the open interval this time, from 1/2 to 2. So my two conditions are satisfied. And so I'm going to go ahead now and I'm going to look for the point that I wanted, where f prime of c equals f of b minus f of a over b minus a. And let's see, a is 1/2 and b is 2. So f prime of c, that would be negative 1 over c squared equals f of b, that would be 2 plus 1 over 2, minus f of a would be 1/2 plus 1 over 1/2. Divided by b minus a, 2 minus 1/2. So I get negative 1 over c squared. And let's see if I can just use a calculator to help me out a little bit here. That would be 3/2 or 1.5 minus 1.5 divided by 0.5. And in the denominator, I've got 2 minus 1/2 is 1.5 or 1.5. And that's negative 1. So if I multiply the c squared over, negative 1 equals minus c squared. C squared is 1, so c is either 1 or negative 1. C equals 1 is definitely within the interval that I'm interested in, so that's a solution. C equals negative 1 is not in the interval, so I'm going to ignore it. All right, it says show the problem using a graph. Once again, I'm just going to do that on a calculator. If I go ahead and put my original function in, it's x plus 1 over x. And as far as a window, I'm going to go negative 5 to 5. That'll be plenty. If I think about the points at x equals 1/2 and x equals 2, that would be about from here to here. So you can imagine that line joining those 2 points. And we're saying that at c equal 1, there's a tangent line that's parallel to that. It seems reasonable to me. All right, last example. We've got the same function, but this time the interval is from negative 1 to 2. And hopefully you can see right away that the mean value theorem doesn't apply, because immediately the function has a discontinuity when x is 0. And we saw above that it wasn't even differentiable there. So here I'm going to say the mean value theorem does not apply. F of x is discontinuous at x equals 0, which is within our interval. It's also non-differentiable, but as long as we've got one thing that doesn't work, we can be done. All right, that brings us to the end of topic F. Or no, G, I guess we're on topic G.